Hello, and welcome to Empowered Learning. This video will be about using the substitution rule to do integration in calculus. So our first example here, we see that we have an indefinite integral, and the integrand is cosine cubed theta times sine theta d theta. And so although what we will do in this video will be mostly computational, we still want to make sure that we understand that whenever we evaluate indefinite integrals, we're finding the most general antiderivative, meaning that we are finding a family of curves that meet the condition of being what the backwards derivative is, if we want to call it that. Also, we're trying to find a general formula for the area under the curve of these functions as well. And so whenever we use substitution, the idea is that there is something in the integrand that if we took the derivative of it, we could come up with the rest of what the integrand possesses. So in this example, we see that if we took the derivative of sine theta, we would just get cosine theta, but that wouldn't help us get anything with cosine cubed theta. However, if we were to allow, let's say, u here to equal cosine of theta, then of course, if we took the derivative of theta with respect to theta, then that would be minus sine theta. And so that helps us out because now we can rearrange everything that we see here to get something with sine theta and d theta in it. So here, if we were to do algebraic manipulation here, we would see that we would have negative du will be equal to sine theta d theta. And so now we know that for all of this, we could replace that with just minus du. And for what we have here, we can replace that with u cubed. So therefore, if we rewrote this, this would just be u cubed du, and we would have negative sign on the outside. So now if we do that, then of course, now the integration is easy because all we have to do is take the antiderivative of u cubed. And if we remember correctly, we know that to do the integration for something that looks like a power function, we just add 1 to the exponent and then divide by that same number. And then of course, since we do not have any limits of integration, we always do plus c at the end to represent that we're finding the most general antiderivative. And so then from there, this would simplify to u to the 4th divided by 4 plus c. And of course, that would just be, let's erase that here. That would just be 1/4. Let's try that again. 1/4 u to the 4th plus c. And now the final thing is we need to substitute what u was. And so u was cosine theta. So that will end up being 1/4 cosine raised to the 4th theta plus c. And this is the answer to our first question here. So let's move on to our next example. So for our next example here, we see that we're trying to look for something so that if we take the derivative of it, we will find the rest of what we can replace in the integrand so that we can make taking the derivative easy here. So in this case, let's look at letting our variable that we're going to use for substitution, which we're going to call u this time, let's let that be x squared. All right, so if we come here, let u equal x squared. And so what that's going to mean is du over dx is going to be 2x, which means that du is equal to 2x times dx. And so as of right now, if we replace x squared with u, we would just have the integral of sine of u. But of course, we need to be able to replace x dx with something. And so we see here that if we were to divide both sides of our equation here by 2, then what we would end up with is 1/2 of du is equal to x times dx. So here we're going to take what x dx is and now just rewrite that as 1/2, and I'll put the 1/2 over here. Du, I'll put that there. And so now from that point, we can take the constant and factor it out of the integral. And now we just have 1/2 times the integral of sine u du. And of course, the antiderivative for sine of u is negative cosine of u. And then of course that'll be plus c at the end. And all that is multiplied times each other. So let's make sure that we know that. So then this is minus 1/2 cosine of u plus c. And now all we have to do is substitute in what u is. And we know that was x squared. So we end up with 1/2 cosine x squared plus c as our most general antiderivative. Now let's look at our next example. And so this next one will actually be doing a definite integral in this case. So we're actually going to have some limits of integration. All right, so in this case, we see here that the expression that we probably want to do u substitution with is right here in the exponent. Okay, so if we let u equal negative x squared, then what that means here is that du over dx is going to be a negative 2x. And thus, what we see here is that if we do our limits of integration, we would have, well, not limits of integration, but just our integration here, we would have e to the u right now. And so we need something to replace x and dx with. So of course, we could come here and multiply both sides by dx. And then after that, divide both sides by -2. And we see that we will end up with a negative 1/2 du is equal to x dx. So here the rest of what we see here will be replaced with negative 1/2 du. Okay? Now, whenever we have limits of integration, the one thing that is different about these type problems versus the ones where we do not have any limits of integration is that you can choose to either substitute what your limits of integration are and translate them in terms of u, or you can wait until after you're done and do it. And so I personally prefer to go ahead and translate everything in terms of the u substitution here, only because I don't want to forget to do that later here. So now that I have this, I also want to take u of 0, because remember, u is a function of x. I want to plug in 0 here. And of course, if I do that, I still get 0 in this case. And if I plug in 1, I see now this is going to be -1. And again, my order of operation, I need to make sure that I do exponents before multiplication here. So now what that means for me is that I have -1 up here and 0 down here. Well, if we remember about our limits of integration, we know that it has to go from lowest number to highest number. So what that means for us is that whenever we do this, we need to flip the limits of integration around, but of course that's going to be the negative of what we were experiencing before. Okay? So now in that, we see that a negative times a negative is a positive, so we end up just having positive 1/2 of e to the u du, and this goes from -1 to 0. And so from this point here, we see that all we have to do is just take the antiderivative of e to the u, which is just e to the u, and we're going to evaluate that from 0 to -1. And so since we've already done, we have written x in terms of u here, we do not have to worry about going back and substituting anything in. So we'll say 1/2, and this will be e to the 0 minus e to the -1. And of course, to finish up, we know that e to the 0 is just equal to 1, and e to the -1 is just 1 over e. So you could keep it this way, or depending upon how you have to express answers, you may want to get this looking a little bit more nice. So if we make a common denominator in between 1 and 1 minus, between 1 and -1 divided by e, that's what I'm trying to say. Of course, we know that 1 is the same as e over e. And so we would just have e minus 1 over 2e. So you could express it either this way here or this way. Either way would be acceptable. All right, so let's look at our next example. All right, so in our next example, to kind of see what we would want to do here, we could come and rewrite this as 1 over x squared times e raised to the 1 over x. And if we wanted to look at this a little further, to do this again and write everything in terms of negative exponents here. And I'm forgetting my dx, so let me not forget that. So when we look at it this way, it's kind of clear what we should use for our u substitution now. We know that if we take the derivative of x raised to the -1, that's going to be a negative x raised to the -2. And we know that because whenever we do the derivative there, we just take whatever the exponent is, multiply it, and then we subtract 1 from the exponent. So, of course, we see that that will give us negative x raised to the -2. So let's get rid of that. So now we're going to say let u equal x raised to the -1, which implies that du over dx now is negative x raised to the -2. And thus, we know that du will be equal to negative x squared times dx. And if we multiply both sides by -1, that's negative up here, then that will be x raised to the -2 times dx. And so now for this portion, we have a direct way to substitute. Okay? So now this means also that we need to go ahead and look at our limits of integration. So u of 1 is going to be the same as 1 raised to the -1, which is the same as 1 over 1 raised to the +1. And of course, that's just 1. When we look at the same thing at 2, so that's 2 raised to the -1, which is just 1/2. So now that we have all that in play, then we know that we take the integral of 1 of e raised to the 1 over x divided by x squared dx. And that's going to be the same as limits of integration going here and we know that we can replace the 1 over x squared, which we're rewriting as x raised to the negative 2 times dx, all that can be replaced by minus du. So we'll do that and put the du there. And then, of course, we have just e raised to the u. And so to finish it off here, we know that our u of 1 is going to be 1. And we know that our u of 2 is going to be 1/2. So again, we're in a situation where these two numbers are not in the order that they need to be in. So to get it in there, we have to do the negative of what we have. And of course, we see that a negative times a negative yields a positive. And so now we just need to take the antiderivative of e to the u, which is just e to the u, and we evaluate that from 1/2 to 1. So now the way that we've done this, we do not have to worry about any back substitution at the end. So all we have to do is substitute in our values here when we do our difference in limits. And so we get that from the net change theorem. And if you're unfamiliar with that, then you can watch the video that I have before this one called Taking Derivatives. Sorry, not taking derivatives, but taking integrals using the definite integral and the fundamental theorem of calculus. So keep on going here. This is just going to be e raised to the 1 minus e raised to the 1/2, which is the same as just e times square root of e. So that would be the exact final answer there. All right, so we've done some integration with some basic algebraic functions. Let's go ahead and turn a new leaf now and start to do something with a little trigonometry in there. So let's look at our next example. All right, so for this example here, if we rewrote this as just the indefinite integral of 1 over 1 plus x squared times tan inverse of x dx, and if we note that whenever we take the derivative of tangent inverse, the derivative of that will be 1 over 1 plus x squared. So it's pretty obvious what we should use for our u substitution here. So we're going to say let u equal tangent inverse of x. And of course, that'll imply that du over dx is 1 over 1 plus x squared, which implies that du is just 1 over x squared times dx. So then we can take all of this and substitute it directly. Okay. Therefore, we know that the indefinite integral of tan inverse of x divided by 1 plus x squared dx, that is just going to be indefinite integral of, not writing tangent there, we're replacing that, so we know that tangent inverse of x now is just u, and we know that 1 over 1 plus x squared dx is just going to be du. So now if we take the antiderivative of u, which is like u to the 1 here, and that would be u to the 1 plus 1 divided by 1 plus 1, and then plus c because we have no limits of integration. So that would end up being u squared over 2 plus c, which will end up being 1/2, and our u, again, is tangent inverse of x. Let's make that look a little nicer. Plus c. And that would be our answer there. But we would have to square that. Yep, so I forgot that. Take that and square. All right, let's look at our next example. All right, so for our next example, it looks like our numerator and denominator are pretty similar. The only difference is our denominator has +3, so we have two terms. And we know that whenever we take the derivative of an exponential function, its derivative is proportional to itself. So, and in particular, if you get what I'm talking about here, if we took the derivative of 2 raised to the t, then this would just be 2 raised to the t times natural log of 2. So that much we already know. And of course, natural log of 2 is just a constant number. So we see that we would have 2 raised to the t taken care of if we took the derivative of this. But we can also take care of it if we use 2 raised to the t plus 3, because of course the derivative of 3 is just 0. So using the denominator covers more stuff, so let's go ahead and use that for our use substitution. So erase these bits here. All right, so we're going to let u equal 2 raised to the t plus 3. And so that's going to imply that du over dt, because remember our variable now is t, and that's going to be equal to 2 raised to the t natural log of 2. Of course, our goal here is to figure out, since we're going to name all of this u, how we can replace this part. And so we can do that by multiplying both sides times dt, and then dividing both sides by a natural log of 2. Of course, that reduces to 1, and we have our direct substitution here. So now when we come up here, we see that the integral of 2 raised to the t over 2 raised to the t plus 3 dt, that is just going to equal the integral of u in the denominator, and of course this would be du, and this would be times some constant 1 over natural log of 2. And of course I'm just going to factor that out. 1 over natural log of 2. And that will just be 1 over u du. And of course we know the antiderivative of 1 over u is just natural log u, because the derivative of natural log u is just 1 over u. So we have our constant number out here. Multiply that times natural log of u, and here we just do a plus c at the end because we have no limits of integration. And so now we go back and substitute what u is. And u was 2 raised to the t plus 3. And we have that plus c. And for the most part, we are done there. We could change this into something different using the change of base rule, but that would be getting too fancy at that point, and we don't think it's necessary, but I'll do it anyway, just so that you can see what it looks like. So if we use the change of base rule here to make this a little bit more compact, I'll go ahead and recite what the change of base rule here in between here. So we want to change from base A to base B. And this is what it would look like. So of course this comes here, that goes there. But now since we're trying to go from this form back to here, this would be backwards. Okay. So because of that, we would say that we would have log base 2 now of 2 raised to the t plus 3, and then that would be plus c at the end. And so that's how that would look. I'm going to clean this up because that didn't look too hot. So this answer here or this answer is acceptable. All right, let's move on to the next example. All right, so in our next example here, if we notice we have tangent cubed theta, and that's multiplied times secant squared theta. And if you're thinking about derivatives, the first thing that you probably should recognize here is that if we were to take the derivative of tangent theta, that would actually end up equaling secant squared theta. So here, it seems like it would be the most logical thing to let our u substitution now be tangent theta, so that when we take the derivative, du over d theta, that would just be equal to secant squared theta. And of course now we'll have a way to be able to substitute this directly. All we have to do is just multiply both sides by d theta. And now we have that direct substitution there. So now, if we were looking at our integral here, this would be the same as the tangent cubed theta would just be u cubed, and then du would just be equivalent to secant theta d theta. So that would be here. Of course, we'll go ahead and move this over. Give us some room here. So now we just have to take the antiderivative of that, which will just be u to the 3 plus 1 over 3 plus 1 plus c. Of course, there's u to the 4th over 4. And that would be, oops, forgot my plus c at the end there. So our plus c, and then that'll be 1/4, and u is going to be tangent theta, so that'll be tangent to the 4th plus c. And that would be our final answer for this example. All right, so for our next indefinite interval, we see that we have square root of cotangent x, and we have cosecant squared x. So what should jump out at us is that if we were to take the derivative of cotangent x, that should be negative cosecant squared x. So we see that we have a positive cosecant squared x in there. So it just makes sense that we use cotangent as the expression for the u substitution. So if we do that, then if we let u equal cotangent of x, then that implies that du over dx is negative cosecant squared x. And of course from there, we know that du, if we multiply both sides by dx, is just going to be negative cosecant squared dx. And finally, we just want secant squared dx, not the negative. So we'll just multiply both sides by negative 1. Okay. So now we have all this business here. We know that when we do our integral here, this is just going to be square root of u, and that's going to be times a negative du. And of course, the negative we will factor out. The square root we will write in fractional exponent form. And we have just a negative integral of u raised to the 1/2 d. So here, that would be 1/2 raised to the 1, I'm sorry, 1/2 plus 1. And of course, we will divide by the same thing here. Make sure that's looking okay. So we have negative u raised to the 3/2 divided by 3/2. And this should be plus c at the end. I keep on forgetting that. So I apologize. Let's make this look a little neater. Just gotta have the plus c on the end. And of course, we're not losing the negative there. Plus c. And now we know that the reciprocal of 3/2 is 2/3. So we got a negative 2/3 u raised to the 3/2 plus c. So now all we need to do is substitute what u is now. And go ahead and put this back in root form. So it'll be square root of u cubed plus c. So u is equal to cotangent x. And that would be that cube. See if I can get a little bit more room there. So cotangent cube x, and then that would be plus c. So that is how we do that integral. Let's move on to the next one. All right, so in this example, we are going back to some definite integrals here. And of course, we see some more algebraic looking functions. So we'll just take the antiderivative of each one of these and then use a net change theorem to evaluate this from 0 to 2. So I'm going to keep everything pretty much together here. Actually, don't need to write that. Here I can go ahead and do the integration. So to do that, I would have x to the 2 plus 1 over 2 plus 1 plus, I would ignore the 2 here and just integrate e to the x. And of course, the antiderivative of e to the x is just e to the x. And so here, when I have 5 raised to the x, that one's going to be slightly different, because we know that in order to get the, we know that the derivative of 5 raised to the x is just going to be 5 raised to the x times natural log of 5. So here we would have to have some factor that has natural log of 5 in it in order to make everything work. So one way we could do that is we could hold off and let's go ahead and evaluate these first two, or at least put it in this form here, going from 0 to 2. And then we could just say this is going from 0 to 2 at 5 raised to the x dx. And so we'll just work on this part. So on there, if we let the u equal 5 raised to the x, then what that means is du over dx. I think it's not cooperating with me here. So that means du over dx is going to be 5 raised to the x times natural log of 5. And of course, if we want to find a way to replace dx, then of course we have to multiply both sides by dx first to get it on the right side. And then of course we would divide by natural log of 5. I think before I said we want to just get dx, we really want to get 5 raised to the x dx. So that's what we're looking for. So that's why that reduces to 1, and we just have basically 1 over natural log of 5 du is equal to 5 raised to the x dx. So now in place of what we see here, we are going to put what you see there. So now that we know that, I'm just going to come here and we're going to finish this up. So now we know that we have x cubed divided by 3 plus 2 e to the x, and that will be plus, let's see here, we want to replace all that we see here with the 5 raised to the x dx. So inside here, this would be just 1 over natural log of 5 du. And of course, since we have limits of integration now, we can also figure out what u of 0 and what u of 2 would be. So I'll go ahead and put that here. Try to get my pen to cooperate a little better with me. And of course, I'll come up here and just do that. So u to the 0 is the same as 5 raised to the 0, which is just 1. And we'll have u of 2, which is 5 raised to the 2, which would be 25. So we're looking at this in here, we know that that's 25. We're looking here, and we know that that's 1. So now we have, let's go ahead and pull out that constant 2. So we have 1 over natural log of 5. It's going to be 1 to 25 of du. Of course, that's like having 1 du. So that means taking the antiderivative real simple. It's just going to be u. No pun intended here. So we're there, and this will be that times u from 1 to 25. Okay? And I forgot about this part. But here we need to still evaluate that from 0 to 2. And yeah, I kind of butchered that because I forgot all about this other stuff here. So let me erase this and write it how it's supposed to look. Let me just pause it for a second and erase so I can have this looking the way it's supposed to. All right, so now that I got that mess cleaned up, we can go ahead and finish this problem here. So, of course, come here and say this is x cubed divided by 3 plus 2 e to the x, and that will be from 0 to 2. And then we will also do plus, and I'll just write this up here before I go down there. This will be 1 over natural log of 5, and that will be u from 1 to 25. And of course, all of that will come down here and finish up. So if we evaluate the first two terms, 0 to 2, and of course, what we get here is we'll get 2 cubed over 3 plus 2 e to the 2. That'll be minus 0 cubed over 3 plus 2e to the 0. I'll clean that up. And then this will be plus. So now we will have 1 over natural log of 5. And inside here we would have 25 minus 1. And of course here, we work this out. This would be 8 cubed plus 2e squared. Now this is just 0. And we know that e raised to the 0 is just 1. So we have minus 2 there. And then I have plus 25 minus 1 is 24 over natural log of 5. And of course, this would be our exact answer. The only thing that we need to do at this point is just combine the 8/3 and the 2. So to do that, of course, we realize that 2 is going to be the same thing as 6 over 3. So, oops, let me erase that. So here we'll say that's the same as 6 over 3. That fraction didn't come out so hot. So here that is 6 over 3. And then 8 over 3 minus 6 over 3 is just 2 over 3 plus 2e squared plus 24 over natural log of 5. And that is our final answer in its most simplified form. All right, let's move on to our next example. All right, so for our next example here, we see that we have 3 different terms in our integram, and all of them, for the most part, look pretty simple. Of course, the antiderivative of sine is negative cosine, antiderivative of cosine is sine. But we see here that we have 5 divided by square root of 1 minus x squared. And of course, if we were to try to come in here maybe and say 1 minus x squared and let that equal u, we know that wouldn't really work because the derivative of 1 minus x squared is just 2x, and we don't have another x in this particular term. So in looking at this, we have to remember that have a negative 1 over 1 minus x squared. This actually equals the derivative for cosine inverse. Okay, and I'll just do that in prime notation. So here, because of that, we could rewrite this as 3 sine of x. Well, let me not do it like that, because I'm trying to break it up as 3 separate intervals. But if I do it that way, then I'm going to have to come up with a lot of constants, and I really don't want to write that. So what we'll do is just write it like this. So we'll say this is a 5 minus 5 times 1 over 1 minus x squared. Of course, all that's inside square root sign, plus, here we'll rewrite that as 1/7 cosine of x. Things acting funny again. That's okay. So all of that is the integram times dx. So now we ignore the constant. Integral of sine is minus cosine. And we know that ignoring the 5, let's kind of put that like that. We know that the derivative of cosecant, so not cosecant, the cosine inverse of x is negative 1 over square root of 1 minus x squared. So the antiderivative of negative 1 minus 1 negative 1 divided by square root of 1 minus x squared. It's just going to be cosine inverse. And then, of course, 1/7 constant, ignore that. Antiderivative of cosine is sine. Of course, once all that's done, we just append the plus c on the end, and that's pretty much it. So we just try to rewrite to make it look nice. And this is what it would look like. All right, so with this next example, we're going to see that whenever we do our substitution, we're going to have to do a little more than just substitute some inside function for u and take the derivative of it and replace the rest. We're also going to have to find a way to be able to manipulate what our equation is when we say u equals, in order to basically cover everything that's in the integrand. So in looking at this, we'll see that we probably should use u is equal to 1 plus 2x. And of course, if we take the derivative of that with respect to x, that is just going to be 2. Because derivative of 1 is 0 and derivative of 2x is just 2. So that means du will be equal to 2 times dx, okay, if we multiply both sides by dx. Now notice here, we're going to be replacing all of this with u, and we only have, we have x times dx here, but here we see we only have a constant times dx. So when we do this and divide both sides by 2, we're going to have 1/2 du is equal to dx. So here we can only take this and replace it with 1/2 du. We still need some way to write x in terms of u. Well, what we also know here is that if we take this equation and we solve for x, then we'll have a way to express x in terms of u. So let's go ahead and do that. So from here, we see that if we subtract 1 from both sides, and then we divide both sides by 2, we will get u minus 1 over 2 is equal to x. So now we have a way to replace x in terms of u. And of course, the last thing that we'll do is we'll take the limits of integration and we will translate those in terms of u as well. So if we plug in 0 into u, then of course we just get 1 there. So this is just 0. And if we substitute in 4 into u, of course in this case, 2 times 4 is 8, so 1 plus 8 is 9. So now we have everything that we need to set this up. So just going to say that everything that we talked about here is actually going to equal, and this will be now u sub 0 to u sub 4 of, now we have 1 over square root of u, and for our x, this will be u minus 1 divided by 2. And for our dx, this will be 1/2 du. And so we pretty much have all this, and we will look at our new integrand in terms of u to be that. So of course, we know our limits of integration now go from 1 to 9. And we know that 1 over square root of u is the same as u raised to the negative 1/2. And here I could rewrite u minus 1 divided by 2 as just 1/2 times u minus 1. And then all that is times 1/2 du again. So all of this is here. And so now we just need to simplify what we have so that once we're done, we can actually take the antiderivatives of these easy and use the net change theorem. So I see that I have 1/2 and a 1/2, that's a constant. So that tells me when I multiply that, I have 1/4. So that is going to be the constant that I take out of the integral. And then what I have left is u raised to the negative 1/2 times u minus 1 du. And of course, u is the same thing as u raised to the 2 divided by 2. And so now when I distribute my u raised to the negative 1/2 to both terms here, I know that whenever I have two exponential expressions that have the same base, different exponents, I can add the exponents. So that's going to give me u raised to the positive 1/2 minus u raised to the negative 1/2, all of that du. And so now from that point, all I need to do is take the integral of both of these terms, subtract, and then use the net change theorem to evaluate them at 9 minus evaluate them at 1. So I have 1/4 here. And we know that the integral of u raised to the 1/2 is u raised to the 1/2 plus 1. And we'll write plus 1 is just 2 over 2. 1/2 plus 1, 2 over 2. And then that'll be minus u raised to the negative 1/2 plus 2 over 2 over minus 1/2 plus 2 over 2. That didn't turn out so hot. And of course, all that is going to be evaluated from 1 to 9. And so from there, just come here. That is 1 right there. So I'll erase that and make sure that that can be seen. That's from 1 to 9. And we'll just kind of loop it like that. Yeah. All right. And so now from there, we'll just keep on going, simplifying. So here we have u raised to the 3 over 2 over 3 over 2 minus u raised to the positive 1/2. Try that again. U raised to the positive 1/2, all that divided by 1/2, and then of course that's being evaluated from 1 to 9. And the reciprocal of 3/2 is 2/3. U raised to the 3 over 2. Reciprocal of 1/2 is 2, raised to the 1/2, and then that's evaluated from 1 to 9. And so at this point, I'll go ahead and distribute our 1/4 to both terms there. And when we do that, 1/4 times 2/3, we know that we have a common factor of 2 here. So this will reduce to 1/2. So we'll just have 2 down here in the bottom. So 1 times 1 is 1, and 2 times 3 is 6. So that will reduce to 1/6. And I'm going to go ahead and put this in root form now. So this will be square root of u cubed. And then minus 1/4 times 2, it just gives us 1/2. And that will be square root of u. Of course, that again will be evaluated from 1 to 9. And so from here, we go ahead and substitute our limits of integration. And so that will be 1/6 square root of 9 cubed minus 1/2 square root of 9. And then using the net change theorem, we do the same thing, but now we just plug in 1 for u. Okay. So now that we have this, of course we know that here 1 cubed is just 1, and square root of 1 is 1. And of course here square root of 1 is just 1. So we know that. So for the second part, we just have 1/6 minus 1/2. For here, we know that 9 is the same thing as 3 squared. So I'm just going to write in this space up here. We know that 9 is the same thing as 3 squared, so we could rewrite what we have here is the same as 3 squared, all that cubed. And so that'll be the same thing as 3 raised to the 6, which is the same thing as 3 raised to the 6 divided by 2, which is 3 raised to the 3. And of course, 3 raised to the 3 is just 3 multiplied times itself, which is 27. So all of this here is just 27. And of course, square root of 9 is 3. So once we're done here, this will just be 1/6 times 27, which is 27 over 6, times 1/2 times 3, which is minus 3/2. And then here, we know that we need to distribute whatever it is that we're multiplying here. So that would be minus 1/6. And then that will be negative times negative positive plus 1/2. And then so from there, we have like fractions here. So 27 minus 1 is 26. So that'll be 26 over 6. Negative 3/2 plus 1/2 is a negative 2/2, or just 1. And so now from here, we know 1 could also be written as 6 over 6, which will give us 20 over 6. And of course, to finish this out here, we know that 20 and 6 both have a common factor of 2. So when we reduce 2, that'll be 10, and 2 goes into 6 3 times. So our final answer here would be 10/3. So a lot of work, but again, a lot of it is just doing a bunch of simplification after we've actually applied all of the substitution coming from u and the derivative, and also substituting the limits of integration, translating everything in terms of u. So a lot of simple computation is basically what this boils down to after we actually substitute everything in and do the integration. All right, so let's look at our next example. All right, so for this one, it'll be sort of the same thing. We notice here that we could rewrite what we have as just 1 over 5x plus 1 dx, like this. And obvious choice for substitution is to let 5x plus 1 equal u. So we're going to let 5x plus 1 equal u, which means du over dx is just equal to 5, because derivative of 5x is 5, derivative of 1 is 0. And this implies that our dx here, well, du is going to equal to 5 dx. And if we divide both sides by 5, then we have 1/5 du is equal to dx. So we have a way to replace dx we can replace 5x plus 1 with u, and we just have a constant of 1/5 that comes out as a result of that. So in addition to that, let's go ahead and translate our limits of integration. So here we'll say u of 0 is going to be 1. Of course, 5 times 0 is 0. 0 plus 1 is 1. And u of 3, once we plug this in, we see that that will be 16. Because, of course, 5 times 3 is 15. So we have everything that we need. So when we come here, this will just be integral of u sub 0 raised to, so not raised to, but the limits of integration are u sub 0 and u sub 3 now. And this would be 1 over u times 1/5 du. And let's make that look a little better. And so now we can take the 1/5 out. We know that our new limits of integration are from 1 to 16. And we just have 1 over u du. And so now we know that the antiderivative of 1 over u is just natural log of u. And we're not going to worry about having u in absolute value signs because all the values that we're dealing with are non-negative. So we're just going to say natural log of u like this, and we will evaluate that from 1 to 16. So that'll be 1/5 natural log of 16 minus natural log of 1. And of course, natural log of 1 is 0. And this will be natural log of 16 divided by 5. And so you can keep your answer that way. If for some reason you need to have your answer is just natural log of a number, then we could go a little further here. Not saying that you have to do this, but if for some reason it's convenient to have everything in terms of just natural log of a number, then we know that what we have here is the same as 1/5 times natural log of 16. And we have a logarithm property that allows us to take this 1/5 and put it as an exponent to the 16 inside the logarithm. And of course, we know that something raised to a fractional exponent is just another way of describing a root. So this would be the 5th root of 16 inside the logarithm. So you could either express your answer this way, which is totally acceptable, or you can express it this way if you really need to have just natural log of some answer. All right, so let's move on to our next example. All right, so for our next example, we see we have an inverse trigonometric function inside our integrand here. So we're thinking that whatever else is inside the integrand as well may be related to the sine inverse function via its derivative. And it actually turns out that if we take the derivative of sine inverse of x, we know that that's actually 1 over square root of 1 minus x squared here. Okay, so we know that there's a direct link. So this actually is going to be pretty clean whenever we do the substitution here. So let me get rid of this right quick. So in our substitution here, let's let u equal sine inverse of x. And so that's going to imply that du over dx is going to be 1 over 1 minus, so 1 over square root of 1 minus x squared. Make sure that covers everything. And so now that also means that du is now going to be 1 over square root of 1 minus x squared dx. Okay. So we have direct substitution here. So we have that, all of this is being replaced by the derivative, and of course u will just be sine inverse. In addition to that, we also know that we need to do the limits of integration here. So in looking at this, we'll also know that u sub 0 is going to be sine inverse of 0, and that will just end up being 0. And u of, what's it, 1/2 is just going to be sine inverse of 1/2, and that is going to end up equaling pi over 6. And so I'll give an explanation for this. So whenever we're dealing with sine inverse, we do need to actually realize what's going on with that. And so from a simple standpoint, since the limits of integration are within the range of sine inverse, then we can just use what's called the cancellation property. So what I'm getting at is this. So when we had sine inverse of 0 equals 0, then of course we can take the sine of both sides and since sine and sine inverse within the ranges of -1 to 1 as far as the y values for sine are concerned, and we're looking at the values from -pi/2 to pi/2 for the angles for sine, and thus whenever we do the inverse, everything's reversed now. So the domain is from -1 to 1, and the range is from -pi/2 to 2. Then within that, we know that we can use the cancellation property, and this actually comes from pre-cal or college algebra, which says that anytime we have a function and its inverse here, if we stuff the function into its inverse or the inverse into the original function, if they are indeed inverses, you should always get x, or what's on the very inside here. So in doing that, we know that sine inverse of x is just going to give us 0, and then this is just sine, oops, I wrote that wrong. So this should be, this should just be x here. Yeah, that's what I meant to write, sorry. So same kind of thing here. And here, I think I have that written right. Oh no, that's still not right. So let me start all this over so that you can see what's going on there. Yeah, I'm just going to get rid of it. So my whole point here is this. If we have sine inverse of 0, let's say if we let that equal x, then if we do sine of sine inverse of 0, then that's the same as sine of x. And of course, the left side here would just equal 0, and we would have sine of x. And of course, if we're looking at the graph of sine, looks like this. And of course, at 0 degrees, 0 radians, we know that sine is equal to 0. And so, of course, it's the same here at 2 pi as well, but we're looking only within quadrants 1 or quadrant 4. And of course, the reason for that is the following. We'll erase this graph. Here, when we look at sine in terms of sine inverse, we're only looking at it from -pi/2 to pi/2. And the reason for that is that from here to here, our function is what we consider to be is a one-to-one function, which means for every x value, you have a unique y value. And it passes both the vertical line test and the horizontal line test. So if we look at it beyond negative pi over 2 to pi over 2, then we get a function that's not one-to-one, and thus it can't have an inverse. So here we need to get rid of all of this. So I'm going to erase this, erase all of this, and we're just dealing with this piece. And of course here that's 0. So 0 to pi over 2, we know in terms of quadrants, that's quadrant 1. And 0 to negative pi over 2, if we're looking at negatives, angles negatively, then we're going clockwise. That would be here, and that's quadrant 4. So I'm mentioning all this because this is the kind of thinking that we have to have whenever we're evaluating this. Now, of course, if you know this already, then that's fine. You can just skip on to the end of the problem. But for those of you that aren't familiar with this, you do need to pay attention so that you know how we're actually getting the answers that we're getting. Okay, because according to what these limits of integration are, that's going to play a role in knowing what your angle answers are going to be, and that's going to be based upon what quadrant you're in. Okay, so for instance, if we were doing this from negative 1/2 to 0, then we would actually be operating in quadrant 4 instead of quadrant 1. And so if we were doing this, my answer to this question, if it was negative 1/2 here, I would have negative pi over 6 instead of positive pi over 6. And so that would be important to answer it that way. So that's why I'm sort of going over this trigonometry review here. Now for sine inverse of 1/2, if we allow that to be x as well, then using the same cancellation property, we could say 1/2 is equal to sine of x. And of course, since sine is positive, we know that we're working in quadrant 1. So that would be, let's see, if this is 1 here, that would be like 1/2 on the y-axis here, which would map to some point here, which would map down in here. And of course, if we look at it from a quadrant perspective, we know we have a right triangle here. We know that sine is going to be opposite over hypotenuse, so this will be opposite 1 here over hypotenuse. And we know that if we have hypotenuse is 2 and 1 is the leg, then this is a 30, 60, 90 triangle where this side is square root 3. And here, pi over 6, which is the same as 30 degrees, is going to be the angle that is opposite of 1. This angle here, where I have this point, will be 60 degrees, or pi over 3, which is opposite of square root of 3. And of course, 90 degrees is the angle opposite of 2. And so from here, we can just go directly and say that x is pi over 6. So that is how I'm getting these answers here. Okay? And this is looking at our sine function here. I'll go ahead and draw sine inverse so that you can see what that looks like. So I'll get rid of this. So when we have this graph of sine restricted from negative pi over 2 to 2, we just basically take all of this and we flip all the x and y values and interchange them. So when we do that, our graph now looks like this. So we have, let's see if I can get that, pi over 2, negative pi over 2, and here we have negative 1 and 1. And for instance, here at this point, we have the graph pi over 2, have the point pi over 2, 1. Now we're going to have in sine inverse the point 1 pi over 2. Okay, so that's going to be here. And so our graph is going to kind of look like this now. So that's what sine inverse looks like. Okay. All right, so I'm going to erase this and finish up the problem here. All right, so now we have some space cleared. We'll go ahead and actually do the integration for this. If you are still wanting to know a little more about sine inverse, I do have videos that go over how to produce the graph of sine inverse with respect to sine, so that you can kind of see how we're looking at the domain and range of that inverse function. So I do have videos on that. Just search for graphing sine inverse and under my name, and it'll come up. All right, so let's finish this problem up now. So we know that we're going to take what we see here, and now we have integral of u sub 0 to u sub 1/2, and we are replacing sine inverse of x with just u, and 1 over square root of 1 minus x squared dx with du. Of course, pretty easy now. Let's get some separation here. And we know that u sub 0 is just equal to 1. U sub 1/2 is pi over 6. U times du. Let's make that look a little better. So now, when we do the integration, u is the same as u raised to the 1. So that would be u raised to the 1 plus 1 over 1 plus 1. And all that will be evaluated from 0 to pi over 6. Of course, that's the same as just saying 1/2 u squared from 0 to pi over 6. Now I'll go ahead and factor out the 1/2. And then we will just substitute in. So we have pi over 6 squared minus 0 squared. And this is us using the net change thing. So we just have 1/2, and this will be pi squared over 36. Of course, this is just 0, so we don't worry about that part. And that will be pretty much it. So we'll have pi squared over 36 times 2, which is 72. And that will be about it. So we'll go ahead and move on to our next example. Winding down. All right, so for this next example, we're wanting to take the definite integral of x cubed plus x raised to the 4 times times tangent of x. But we see here that the limits of integration are from negative pi over 4 to pi over 4. And another thing that is sort of piquing our interest here is that we have x cubed, which we know is an odd type of function. And we also see that tangent x in the next term is an odd function as well. So we're thinking that this function may be odd, and if it is, then we know that we may have a special property going on here. And I'll use just the basic sine function as an example. So here, if we were looking at sine for, let's say, this first period going on the positive x-axis and the negative one, let's say if we wanted to find the area under the curve from here to here. So basically from negative pi over 2 to pi over 2. Well, we know here that since sine is odd, then we know this function here is going to rise the same way that one dips. And of course, the area under the curve above the x-axis is going to be the same as the area under the curve below the x-axis. So in knowing that, we know these areas here, even though one is positive, one is negative, would be the same. So the net area, which is what we would do when we would take the integral here, would actually be 0. So we're actually thinking that in this case as well. So to verify that that is the case, then we're going to test to see if this function here is going to be even or odd. If it does turn out to be odd, then we can just make the assumption here that this integral is going to equal 0. So let's go ahead and test it out. All right, so in us testing it out, we're going to replace negative x everywhere where we see x in our function here. And I know this should look very familiar to you all because this is a concept that comes from pre-calculus or college algebra, depending on what you took. And we see that negative x cubed is just going to be a negative x cubed like this, which we translate this way. Since we have negative x raised to an even power, that will stay as just positive x to the fourth. But tangent is an odd function because we know tangent is comprised of sine and cosine. In particular, tangent is sine x divided by cosine x, and sine x is an odd function like what we have just described here. Okay, so that makes tangent odd. So now we see that we just have negative x cubed minus x to the fourth times tangent x. And this is, if we factor out the negative there, we will have this. And what we have here is exactly what f of x is. So we end up having minus f of x. So we started off with f of minus x, and we end up with negative f of x. So that lets us know that our function is odd, because anytime we replace negative x for a function and we end up with the negative of the original function, or put another way, if we have some point xy on our graph and we replace with negative x, we also have a point negative x, negative y on the graph. If it's odd, then we know that it's an odd function. And so just for general purpose here, even functions look like this. So you replace negative x everywhere where you see x, and you get the original function back again. Or put another way, if you have a point xy, then that implies that you also have a point negative xy as well. And so cosine is a good example of an even function, even trigonometric function. So with all that being said here, we know since f of x is an odd function here, when we go and evaluate this limit, there's not much for us to do. And of course, if we were to try to do something, it wouldn't have been impossible. It just would have been a very long, tedious process. But we know since that function's odd and the limits of integration are kind of symmetrical in a sense, then we know that that final answer is going to be 0. And so we saved ourselves a lot of time by doing some thinking first before just doing stuff. Okay. All right, so let's move on to our last example. And so this is our next example, and we actually have one more example after this. So I know I said this was our last one, but we actually do have another one. So I want to make sure I get as many of these in as possible, so you guys see as many different types of examples as possible. All right, so here we are trying to figure out what the integral of this is. And of course, we see that our limits of integration are from e to e raised to the 4. And remember, e is just an irrational number that's approximately equal to 2.712. So the reason why this is written in terms of e is because we're dealing with natural log here, and it actually makes our life easier when we write things. Whenever we're dealing with natural log, if we can write numbers in terms of e, it makes it easy. And that's mainly because of this logarithmic property. And so it says that anytime you have log of something raised to a power, you can basically take the exponent out. So that's one of the properties. Another one, which is probably the one that we will exploit the most, is this one. So log base a of a raised to the x is just x. And so you can either do it this way in a two-step process, or here just go directly here and do it. Let's say if we had natural log of e to the fourth, then of course this is the same as log base e of e raised to the 4, which is just 4. So that's one of the reasons why, if we can write numbers in the base of whatever logarithm that we're dealing with, it actually makes life easy for us. So that's why you see those e's there. So the problem looks more difficult, but it's actually there to make the problem easier to do. All right, so we need to find something to substitute. And so just by looking at this, we want to rewrite this to be the same as 1 over x times 1 over square root of natural log of x times dx. And so what I would do here is I would actually let u equal natural log of x. And I only say that because we know that the derivative of natural log of x is what? Yeah, that's right. It is 1 over x. And so now we have du is equal to just 1 over x dx. And so now we have a way to replace all of this. And so the last thing that we need to do is change our limits of integration from in terms of x to in terms of u now. So u of e is just going to be natural log of e, which is just 1. And we know that u of e to the 4th of natural log of e to the 4 is just going to be 4. And that's because of logarithm properties I've mentioned earlier. So in particular, for this first one here, we know that log base e of e is equal to 1. That's actually what natural log means. And for this second one, we have log base e of e to the 4, which is just 4. And both of those come from this logarithmic property that I have talked about earlier. All right, so let's get rid of that and finish the problem here. All right, so now we can take all that we see here and we'll write this as u of e and u of e to the 4th. That's our limit of integration. And we know that have 1 over square root of u for 1 over square root of natural log of x. And the 1 over x dx can just be replaced by du. And of course here we know that u of e is just 1. U of e to the 4 is just 4. And 1 over square root of u can be rewritten as u raised to the negative 1/2 du. So from here you see integration gets quite easy. And so if we take the antiderivative of u raised to the negative 1/2, that's just going to be u raised to the negative 1/2 plus 1. And we'll write 1 as 2 over 2. Negative 1/2 plus 1. And that will be evaluated from 1 to 4. And we'll come here and finish it up. So the numerator simplifies to u raised to the positive 1/2 over positive 1/2 goes from 1 to 4. 1 divided by 1/2 is just going to be 2. And so we'll factor that out. U raised to the 1/2 from 1 to 4. And we know that u to the 1/2 is the same thing as just square root of u from 1 to 4. And now we just have square root of 4 minus square root of 1. Square root of 4 is 2. Square root of 1 is 1. So we have 2 minus 1. And of course, that's just equal to 1 on the inside here. And our final answer is 2. So you see, once we actually do the substitution here, this problem turned out to be relatively easy, even though it looked like it was difficult. All right, so let's move on to our last example now. All right, so for this problem, we have cosine x times sine of sine x dx. And we're taking the integral of that from 0 to pi over 2. So in looking at this, we see that our innermost function here is sine x. So let's just kind of take a chance on that and use that as what we're going to do our u substitution for. Now, it makes sense because we know that the derivative of sine x is cosine x. So here we know we have a way to replace at least cosine x dx. And since sine x is actually being used as a variable for its outer function or outside function sine, we're in good shape here. So let's say du over dx is equal to cosine of x, which means that du is cosine x dx. And now that we have that, we only need to replace the limits of integration now, or translate them in terms of u. So now we have sine of 0, which is just 0. And we have sine of pi over 2. And we know that that's just going to be 1. So now we come and rewrite everything. This will be u of 0, u of pi over 2. Let's make that look a little nicer. And then we'll have our cosine x dx. All that will be replaced by du. So we'll have sine of u, and then the cosine x dx gets replaced by du. So from here we know that u of 0 is 0 and u of pi over 2 is 1. And that will be from the sine of u du. So now from here, we just do the antiderivative of sine, which is minus cosine of u. And we will do that, evaluating it from 0 to 1. We'll go ahead and factor out the negative there. And now we just have cosine of 1 minus cosine of 0. And of course, cosine of 0 is just 1. And cosine of 1, of course, is a value. We won't be able to find an exact value for it. So we'll just leave it as cosine of 1. And so this will be minus cosine of 1 plus 1, which would be the same as 1 minus cosine of 1. And of course, you could type in 1 minus cosine of 1 in your calculator and get an approximation for it. Make sure that when you do that, though, that your calculator is in radians. Because again, anytime we deal with trigonometric functions and we're doing real number type stuff with it, like how we're doing here, your arguments or your x values that you deal with for cosine must always be in radians. So, all right, so this is what the final answer is in its exact form. And so I hope that this video has been very informational. Hope you saw a lot of examples that help you out, regardless of whether you're just studying calculus on your own or if you're in a course. And again, I appreciate you checking this out, and check out some of my other videos if you need to. And if there's anything that I don't have that you need for me to do, just send me a message and I'll try to get it done as soon as possible. Thanks. Take care. All right, let's move on. All right, so we're back to doing some definite integrals here. And so now we see that we have a situation where we have square root of something in the denominator, but we also have something in the numerator that we may be able to work with here. Okay? So